Assalamualaikum, my name is Muhammad Zikri Hakim. So today I want to present to you DC chopper or DC to DC converters. Okay, so this is the table of content. The first one is basic principle of DC chopper. The second one is step down buck choppers. And the last one is step up boost choppers. Okay, for basic principles. A chopper is a static device that converts fixed DC input voltage to a variable DC output voltage directly. A chopper may be thought of as DC equivalent of an AC transformer, since they behave in an identical manner. As chopper involve one-stage conversion, these are more efficient. The power semiconductor devices used for a chopper circuit can be power BJT, power MOSFET, GTO, or force commutated thyristor. These devices in general can be represented by a switch SW with an arrow as shown below. Okay, so this is the circuit. So this is the switch or SW, and this is the arrow. Okay, when the switch is off, current can flow. When the switch is on, current flow in the direction of arrow only. The power semiconductor devices have on state voltage drop of 0.5 volt 0.5 volt to 2.5 volt across them. As stated above, a chopper is the DC equivalent to an AC transformer having continuously variable turns ratio. Like a transformer, a chopper can be used to step down or step up the fixed DC input voltage.
So this is a step down or buck for chopper. As we can see, this is a circuit of buck converter and circuit when switch is closed, and then lastly we have a circuit when switch is open. You can see the difference is at the S. So this criteria of step down or buck for chopper. Diode is reverse base. Switch conduct inductor current. This result in positive inductor voltage VL equal to VD minus VO. And lastly, it causes linear increase in the inductor current, which means VL equal L DIL over dt to IL equal I over L VL dt. And as we can see, this is a circuit and a waveform for step down of chopper. And then the switch turn off or open it for step down or buck. First, because of inductive energy storage or IL continues to flow, diode is forward bias and current now flow freewheeling through the diode. And lastly, the inductor voltage can be derived as VL equal to negative VO. And then there's a circuit of switch turn off. As we can see, the S at the circuit is opened, and then there's a waveform of switch turn off. And then steady state operation. As we can see, the graph for IL for unstable current is increasingly, and then graph for decaying current is decreasingly, and for steady state current we can see the graph is steadily. And then steady state operation require that IL at the end of switching cycle is the same at the beginning of next cycle, that is the change of IL over one period is zero, or IE. And then as we can see, this formula, which mean IL or closed plus IL opponent equal to 0. And next, for switch turn on or close, there's a formula which means VL equal VD minus VO equal L DIL over DT to IL DIL over DT equal VD minus VO over L. So derivative of IL is a positive constant. Therefore, IL must increase linearly. From figure, there's a formula as shown at the slide. And for switch opponent, there's also a formula which means VL over VI, VL equal to negative V O equal L DIL over DT. And there's some more familiar at this slide. And then average maximum and minimum inductor current. This graph for IL. So you can see the graph for average inductor current or equal average current in RL, which means IL or equal IR equal VO over R. Maximum current, this formula, as you can see, the formula of maximum current Imax. And for minimum current, I mean we also have the formula. And the inductor current ripple is equal to I max minus I min. So for output voltage ripple, KCL, capacitor current, is IC over IL plus IR. The charge can be written as Q equal CVO to Q equal CAV to OAVO equal AQ over C. Also, we can use a triangle formula as shown at the slide. And ripple voltage peak to peak also have a formula. And lastly, so the ripple factor, we have also a formula shown at the slide. And now some information that ripple can be reduced by increasing switching frequency, second increasing inductor size, and lastly increasing capacitor size. And at the right we can see the circuit of output voltage ripple and the graph or waveform. And then basic design procedures. Uh, we have a graph and calculate D to obtain the required output voltage, and select a particular switching frequency F and device, preferably F is bigger than 2 kHz for negligible acoustic noise. Highest Fs result in smaller L and C, but result in higher losses. Reduce efficiency, larger heatsink. And lastly, possible device, MOSFET, IGBT, and BJT. Low power MOSFET can reach megahertz range. Next, calculate L min. Choose L more bigger than 10 L min, or double bigger for 10 L min, and calculate C for ripple factor requirement. Capacitor rating must withstand peak output voltage. Second, must carry require RMS current. Note for RMS current for triangular, W over F is IP over 3, where IP is the peak capacitor current given by a triangle IL over 2. Caps can be used. Lastly, wire size consideration normally read in RMS, but IL is known as peak RMS value. For IL is given as IL RMS equal to, as we can see the formula at the slide. Next, average output voltage current for step down chopper. The average or DC value of the output voltage is given by VO equal VI multiplied by D, which means PO equal PI, VO IO equal VI LI, LO equal VI LI over VO equal VI LI over VID, and IO equal LI over D. And then this is a basic design procedure for step down chopper. Circuit shown in figure 5.4. The switching frequency is 25 Hz and tone 3 ms. If the output voltage is 6 voltage, what is the supply voltage? Calculate the DC value of the output current and input current in 3A. So as we can see, this figure of 5.4, and then the solution is as shown at the slide. Next, this is driving a DC motor with step down chopper. For A is a circuit of transistor on, and B is a circuit of transistor off. And then DC is being driven in a PWM mode. When the transistor is on, a current flow through the armature. When the transistor is off, the current is circulate through the diode. And then the switching frequency is usually very high to ensure smooth current flows through the motor. Typical switching frequency used in DC chopper application for DC motor range from 20 to 50 kHz. And then this is a circuit construction of step down chopper. This is an example, as we can see from figure 5.7, a simple simplified step down DC chopper circuit. Sorry for the blur image. And figure 5.7 show a circuit diagram of a very simple step down DC chopper. The PWM signal is generated by an stable multi-vibrator or oscillator consisting of three transistors Q1, Q3, Q2, and Q3, and the switch element for the power circuit of A Darlington pair is Q4 and Q5. Next, the S-table multivibrator of this circuit provide a fixed frequency control of about 1 kHz, and the pass wide ratio, the T cycle is adjusted by varying the ratio R1 and R2 using the restat of 10 kilo ohm.
Okay, for the last one is step up boost choppers. In a step up chopper circuit, the output voltage can be several times higher than the input supply voltage. The inductor is used to provide a smooth input current. Some ripple component is actually included in the input current, but is negligible if the switching action is achieved at very high frequency. Capacitor C is necessary to reduce the ripple in the output voltage and smooth the current supply to the load. Okay, so the first one is the circuit of boost converter. The second one is circuit when the switch is closed. And the last one is circuit when switch is open. So basically when the circuit is closed, the current will be flow through here. Okay, so this is when the switch is closed. When the switch is closed, the current will be flow. So this is the calculation. So this is the calculation for this circuit. So the total is VD dt over L. Okay, so this is the circuit when this is the calculation when it's open type. So this is VL equal to VD minus VO equal to L DIL over DT. DIL over DT equals to VD minus VO over L. And the total will be VD minus VO in the bracket and 1 minus DT over L. Okay, so this is the steady state operation. So this is the calculation for steady state operation. Boost converter produce output voltage that is greater or equal to the input voltage. Alternative explanation. When switch is closed, diode is reversed. Thus, output is isolated. The input supplies energy to inductor. The second one is when switch is open, the output stage receive energy from the input as well as from the inductor. Hence, output is large. The last one is output voltage is maintained constant by virtue of large C. Okay, so this is the average, maximum and minimum inductor current. So input power equals to output power. So VD times ID equal to VO squared over R. And the average total will be current L equal to voltage D over 1 minus D squared R. For the maximum one is current max total to current L and then plus this, and then this is the total for, so this is the calculation for maximum inductor current. For minimum current, we need to find the minimum current, so we can calculate the calculation here. Okay, so this is the L and C values. Okay, for CCM, this is sorry. For CCM, this is the calculation for the CCM, and this is the calculation for ripple factor. Okay, so next one is circuit construction of a step up chopper. Okay, so this is the figure 1 as shown here. Figure 1, a simplified step up DC chopper circuit using an stable multi-vibrator as the PWM signal generator. Okay, figure 1.0 is a step up converter that converts an input of 12 volt to a voltage from 13 volt up to 40 volt with a switching frequency of about 1 kHz. The same stable multivibrator or oscillator as before is used. Okay, I think this is all. I think this is it. Thank you. Assalamualaikum.